I am today in a lab of particle physics, actually in France, outside of Paris. Actually, a lot of our collaborators on Atlas Experiment are from this lab, and I've been here a few times for various meetings. So you guys have an exam that's due on Friday. I kind of feel bad because I've been away and haven't had a chance to assess how you guys are doing. So what I'm going to do today is at class time, I'm going to start a Google Hangout session, and I'll send an email with the link to that Hangout session to the list, and then you guys can join that Hangout session, and we can talk about the exam, and I can answer any questions that you guys have. What I want to do today also is give you a lecture on basically the physics behind everything in the challenge. I'm not sure if this stuff is necessary for you to be able to technically do the challenge and the exam, but I think it will certainly help you understand what's going on a little bit and just give it more meaning to what you're doing. I did post everything on the wiki, so the notes that I was going from for the past few lectures when I was there are here posted, and then the slides for today are here posted. Okay. All right, so let me get started with this. All right, so I'm going to talk about Higgs or tau tau as a measurement in Atlas, describe most of what was done there, and then I'll tell you, then focus on the Higgs ML challenge a little bit and the specifics, okay? So if we want to talk about the Higgs, we have to think about how we actually make the Higgs at LHC. And there you have to think about, what are the processes that would end up in the Higgs. And there's various ones, but there are four of them that are very important. And these are the diagrams that represent those processes. You can have two gluons, and they can exchange in this triangle, which is actually a top quark. They can exchange top quarks, and then you can end up having a Higgs boson come off. The reason that there's a top quark here is because the top quark is the Higgs coupling to things is by mass, and the top is the heaviest thing in the Standard Model, heaviest elementary particle in the Standard Model. So that's why it appears here. You can have something called vector boson fusion. So you have the two quarks that are coming from each of the protons. They exchange a W or a Z, and they give off a Higgs. And in that exchange, the W or Z, they give off additional jets. There is also, you can have quark fusion, where you have two quarks turn into W plus H, is associated production, where you make a Higgs with a W or a Z. And then there's also gluon fusion, where you can have the Higgs made with TT bar. So here this is TT bar associated production. Associated production refers to the fact that you make the Higgs along with something else. So these are the four dominant Higgs production mechanisms at LHC. Now, before we observed the Higgs and we didn't know what the mass was, we had to understand what the production cross-section, which if you multiply by the luminosity as I described in class, gives you the rate. So we have to understand what that cross-section would be, and that cross-section heavily depends on the mass of the Higgs. Now we know the Higgs is now 125, so we're sitting around here in the production. So on the left plot here, when you have the Higgs mass versus the cross-section. And what you can see is that for a fixed center of mass energy, and this is for 7 TeV, which was the beginning of the first run of the LHC, the Higgs cross-section falls as a function of mass. So the heavier the Higgs, the harder it is to make that Higgs. Makes sense. And then how the different processes sort of contribute to those. Okay. Now, once you've made the Higgs has to decay, and the Higgs decay modes also depend on the mass. For example, if you are above the mass of twice the mass of the top, then the Higgs could in principle decay to the top. But if you're below that, they can't decay to the top. And as you scan through the mass, different processes become possible or start dominating and so on. So here you can see the decay of the Higgs, which is the branching fraction. So a branching ratio is, if you think about all decays of the Higgs, and you then look at branching ratio is what fraction of all the decays go to a particular final state. So for example, the The B quark after the top, the B quark is the next heaviest fundamental particle in the Standard Model. So its coupling to the Higgs is the biggest. So you can see the Higgs BB bar cross section. So there's a Higgs going to the B, two B's, and that cross section I meant branching fraction is very, very high. Now that starts to fall as other mechanisms become possible. So for example, the W, which is heavy, if you have enough mass to start decaying into one real W and then one virtual one, which I'll describe in a second, or two real W's, then that cross section starts to eat into that decay branching ratio, starts to eat into the branching ratio for the BB bar. So that starts falling and the WW goes up. There are other processes, of course. So here you can see, for example, WW versus ZZ. Again, there are thresholds of when they become possible, where we can make one W versus we can two Ws, as the Higgs has enough mass to be able to decay into those particles. The next relevant thing is, for example, the tau tau, which is what we're going to talk about, and the glu glu. These are the cross sections for those. And CC bar, and Z gamma and gamma gamma. Now you can see the gamma gamma, which is very, very small branching ratio, sits over here, but it's actually, interestingly, one of our modes that we observed it. And so let's then think about now, here on the left side we had the production. Here, once we produce the Higgs, we're looking at what it can go into. But in terms of the rate of what a final state you see, you basically have to take the product of the first plot versus the second plot. So here now you see the cross-section times the branching ratio for different processes. And now if you look as a function of the mass, or again we're sitting about 125 TeV, if you think that different production mechanisms and whatever all put together, you can get then the full rate of a final state, observing final state. So you can see here that a tau tau has a very, very high rate, where it's sitting over here. Something like, I'm trying to find BB bar alone. So these are different final states of BB bar, so I can't find them alone, it's not on here. And you can see basically this modifies it, the multiplying these two modifies it. And really this is what you want to look at, which is, at 125 GeV, this is the effectively the rate or the number of Higgs to that final state that you would observe. Okay, so let's go to the next slide. Now, before we discovered the Higgs, there was good reason that the Higgs was there. First of all, the Standard Model is, Higgs, as we explained in class, is a fundamental linchpin of the Standard Model. So the Higgs isn't there, everything kind of falls apart. So therefore, almost any measurement you do of Standard Model quantities have some component that has to do with the Higgs. And so if the Higgs picture isn't there or isn't right, then you expect some things to not work. So on the right side here is a variety of parameters and measurements you can make in a Standard Model, which are in principle very sensitive to the Higgs and the existence of the Higgs and the mass of the Higgs. And the point that here is being made is that if you take what we actually get, what we measure from what we expect the thing to be from a global fit over this area, you can see everything is sort of around here. Now some things have a fluctuation. So for example, this is 2.5 sigma up, but that's just the definition of a fluctuation, and that, but there's no statistical significance deviant of any of these measurements from what is expected. Basically, these measurements tell you that the Standard Model puts together with the Higgs picture. But on the other side, actually, if you look at the mass of the W versus the mass of the top, those have also corrections that come from the Higgs mass. And so therefore, they're actually sensitive to the Higgs mass. So you can turn this around, and you can go and measure the W and the top mass, and based on that, you can work backwards and try to guess what the actual Higgs mass should be. And so this is actually what they did. So here you can see that you make precision measurements of W and top mass, and these ellipses correspond to, at different points, 2009 and 2012, where they believe the Higgs mass should sit if the Standard Model picture of everything is consistent. And here, if you look at here's a range that corresponds to the Higgs mass of between 115 and 127 GeV. So you can see the 125 GeV, which is somewhere in this range, just barely clips this bottom. This is where the Higgs ended up being. Okay. Now, in the standard model, if you do a global fit and try to get what the most likely Higgs mass would be is 95 plus 30 minus 24, which certainly covers that. This is all from indirect evidence. And in fact, they directly searched for the Higgs at the LEP, and they were able to push the energy of the LEP all the way up as far as they could, and they got up to a limit on the Higgs mass of up to 115 GeV, about 10 GeV below where it ended up being. Okay, so that's the situation before we discovered the Higgs, that we suspected that it should be around this, a certain mass, and we hadn't seen it up to 150 GeV. Okay, so let's talk about discovery. So we discovered the Higgs in 2012 at 125 GeV with 20.3 inverse femtobarn data. Remember this inverse femtobarn? This is femtobarn as a unit of cross-section, which is a unit of area. And luminosity is an inverse cross-section, so that you can multiply by cross-section and you get the rate. So if I take the cross-sections from before and multiply by this integrated luminosity, it will tell me how many Higgses I would see. Okay, so it was discovered there. So let's talk about how it was actually discovered. It was discovered in a combination of 3 different final states. There is the Higgs to gamma gamma final state. There is the Higgs to Z star state, which ends up in 4 leptons. Z is the key to 4 leptons. Now the star here says that actually the Higgs at 125 GeV is not heavy enough to be able to produce 2 real Z's. But as you have tried to explain in class, you can actually have virtual effects where the Z is only there, that contributes to a diagram and is just there for a very short time due to uncertainty principle, but and isn't a physical Z. So here, these are decays where the Higgs gives you 1 real Z and gives you 1 sort of virtual Z. Both of those ended up in 2 lepton final states, so you get 4 leptons. And then there is the Higgs to WW star, similarly, where the W's can decay to a lepton plus neutrinos. So the 2 ends up being 2 leptons plus 2 neutrinos. So those are 4 final states that were observed. So let's talk about a little bit of why these final states. So if you think about it, the Higgs again couples to the mass. So the top, it should couple to the top the most. So anything that has to be at the top with Higgs, the rate for something like that is high. Now, since the top is 175 GeV and the Higgs is 125 GeV, you can't have the Higgs decay into top, and typically you have to decay into TT bar. So you certainly don't have enough energy for that. So where the top comes in is then it's not in the Higgs going to top, but in fact top going to the Higgs in sort of the production mechanisms that we talked about. So for example, the production mechanisms I show over here, this is usually a top in the loop that's here. Okay. There's the next heaviest things that you can have below the top is the W's and Z's. These are about 80 and 90 GeV. This is what we observed. Now what's interesting that these are the force carriers of W and Z. So this is actually, we're observing the Higgs through the gauge boson. These are called gauge boson coupling. And so this means that seeing it in this final state doesn't tell us the Higgs is this Higgs that we expect, because we haven't measured the decay of the Higgs into fermions, into, for example, the quarks and the leptons in particular. The next heaviest thing in the standard model is the B quark. Now, the B quark, as I showed earlier, that is the highest cross section that we have in terms of, branching ratio. But it turns out that the BB final state is a particularly difficult final state to be able to pick out of the background. And that's due to a couple of reasons. One is that the B's appear as there are quarks, and so as I described before, the quarks turn themselves into jets. So you get a B quark come out, but what happens is that turns into a spray of secondary particles, and that's what you observe. Now, so you get the B quarks inside a big jet, and typically you call that a B jet that you see. But jets, you can actually have light quark jets that look very, very similar, and those are copiously made the LHC because, well, most of the time it's QCD processes. You have a quark hitting a quark, something happens with QCD and ends up in quarks coming out, which turn into jets. So that's what QCD is mostly made at LHC. And so, because it's difficult to distinguish B quark jets from the light quark jets, then the Higgs to BB becomes very difficult to see, actually. Even though the branching ratio is really high, you can't experiment to see it. Other issues are that if you try to, for example, calculate the mass of the BB system to get a Higgs mass, the energy resolution on a B quark jet is not going to be as precise as, for example, as a lepton or as a photon. Therefore, that energy distribution. So, for example, this peak that you're seeing here, it's extremely wide. Therefore, it's hard to stand out because it's so broad. It's hard to see it standing above the background. Okay? So the next thing is the tau tau. So after the B, the tau is the next heaviest thing in the standard model. Now, this is interesting because if you can see this tests the lepton coupling. And this has not been observed. There's some evidence for it, and I will show you. But this hasn't been observed, and this is the decay we're talking about. The next one of interest is a gamma-gamma. And as I showed, the gamma-gamma, the branching ratio is very low. But in a complete opposite situation to the BB, photons can be measured very, very cleanly. They can be identified and measured very cleanly with very high resolution in their measuring their energies. Therefore, you can make plots like this, and this is why the gamma-gamma is is one of the discovery channels. It's not because the Higgs decays to that a lot. It's because all the backgrounds to that can be controlled because you can see the photons really well. In fact, one of the most important design characteristics of the photon of our detector was the electromagnetic calorimeter and its sensitivity to this final state. It's one of the most important things that happen. But the photon is also a gauge boson. It's just a lighter version of the Z in the standard model. So this is observed, and this is the W's and Z's is how we observe it. So it shows that how we've actually observed the Higgs has been only through processes that have to do with the gauge bosons. Now, you may then ask, then what happens to the fermions and leptons? Do we know that if that all works out okay? For the fermions, we think it's okay because the production mechanisms, in fact, go through fermions, through the quarks. So we know the quarks come together and they end up Higgs. And since the rates of seeing the Higgs in these other final states has been consistent with what we expect from the calculations from the production mechanisms, which assume the fermion connections, we have indirect evidence that the fermion or the quark couplings are okay. But we don't have any evidence of the lepton couplings being okay. All right. I just wanted to show over here the cross sections for different processes. So glue to Higgs, for example, has a cross section of 20 picobarn. The vector boson fusion, which is this process, is about 2 picobarn. It just gives you the relative size of the various processes. Okay. The associated production is about 1, and this shows you the branching ratio as a Higgs to BB is about 57%, tau is about 6%, mu, which is about 0.2% and 0.02% and so on. Okay, gives you a picture there. All right, so let's talk about the Higgs to tau. So as I said, the Higgs to tau final state is interesting because if you see this, it tests the coupling of the Higgs to the leptons, and since the tau is the heaviest lepton, it's got the highest branching cross section. But the problem is the tau itself is not a stable particle, and it decays to other particles, and as I described in class. And so some large fraction of the time, the tau decays into, it's called one prong, which means that one sort of object comes off. So one prong hadronic means that there's for example, a pion that's coming off, plus neutrinos that we don't see. Some other fraction of time, it decays to a lepton plus neutrinos. And then there's also three-prong hadronic decays where you have 3 pions. You can see, and then there's other decays. So that's all the different decays of tau. Now, in the Higgs to tau event, you have 2 of those taus, and each one of those taus can decay in one of these ways. And so you have a variety of different final states that you could observe, ones with, either with leptons or with hadrons here, with the H corresponding to hadrons being either pions or kaons and so on. Okay, And so then if you want to think about, if you think what final states you can end up, what happens is that about 41% of the time you have sort of this hadron, or maybe 42, that's inconsistent here. You have the taus decaying into hadronic final states. You have some 20 or about 26% of the time, it's going to a hadronic plus, so one is decaying hadronic, so give you pions, and one is decaying leptonically, and this is the electron and the muon, so you put them together, that gives you this number. And then you have some smaller fraction of the time, it's decaying to either mu mu, E or E mu final states. Okay, so that tells you what the possible final states are. Now, for the Higgs ML challenge, the focus has been on the lepton hadronic final state. Okay. The difficulty with taus is that tau decays all involve neutrinos, and so we don't see all of the final state particles of the tau decay. Therefore, it's difficult to reconstruct the tau mass itself because you don't see anything. And in fact, in these events, we have two tau, so you have and multiple neutrinos, so it makes it particularly difficult to be able to estimate the mass of the tau. It requires you to use the measurement of missing energy, and to be able to infer the mass of the Higgs and the tau somehow. So you don't have great resolution of the mass somehow. Now, all of these have leptons in the final state of some sort, and if you count the tau as a lepton. Now, the other aspects of this is irrelevant. The dominant process for this particular decay in terms of production is the vector boson fusion, which goes something about 60% of the production mechanism. Now what's interesting is that, so this is the diagram here in the bottom left for that. So you have two quarks exchanging, sending out W's, which then merge to give you, fuse to give you the Higgs. But in that process you get two other quarks that come off. Now these other quarks turn into jets. And because of the way that this diagram works, these jets tend to be in opposite sides of the detector. These tend to be very forward, means that high eta, high pseudo-rapidity, and that there's a big gap in terms of these two. So this one of them would be forward in one direction, and the other one would be forward in the other direction. And so a good way of finding this final state is by just looking for events where you have whatever you want to see on the Higgs plus two jets that are separated, two very energetic jets that are separated from each other in eta, and there's this rapidity. Okay. Another way that this can be made is also then this gluon fusion diagram. Here you can have radiation of additional gluons, so you get jets and then you get your Higgs. Very similar. There, what happens is that happens at higher energy, so what you get is more boosted Higgs in that case. So if you have Higgs that are really boosted and going very forward, they have a PT over 100 GeV or so, and there, then this process dominates over everything else. Okay. All right. So, and I mentioned that for example, we're looking at the lepton hadron final state. All right, so now let's talk about the backgrounds to this particular search. So I'm talking about Higgs to tau-tau search, okay? First of all, the Z can decay to a tau-tau, and the Z sits around 90 GeV. The Higgs is about 125 GeV, but as I explained, we don't measure the tau kinematics very well because of the neutrinos, and so we can't measure the Higgs kinematics and the Higgs mass very well. So we have a very poor resolution. So if you look at this plot here, this is actually the actual result of the Higgs tau-tau search, but it's very evident here that what you're primarily dominated by is this peak here that has to do, which is this Z to tau-tau, and then if you look at it, it's very, very broad. It's not a very skinny thing, so it sits at 90 GeV, but it's got a tail that goes all the way up to 150 GeV. And the Higgs, 125 GeV Higgs, is sitting over here somewhere. And so it's, and actually just as to scale, you can see that it's a very small amount compared to everything else. So the most dominant background is the zeta tau-tau. And this is an irreducible background in that it's got the same final state as you. Therefore, there's really no way for it to distinguish it from anything else besides from the mass itself. And the mass resolution is not very good, so you have a very hard time distinguishing this from the actual Higgs to tau-tau. Other types of backgrounds come from processes where there's W's or top in the final state. So you can look here, for example, here is a process where you have two tops the two tops going to W's, W's decay to lepton plus neutrino, or to two jets, depending on how you go. And that can end up giving you the final states that or mimic the same final state of Higgs to tau tau. So if you just go through these are various diagrams that can do this. And there's reducible backgrounds in the sense that there are backgrounds where it's due to some mistake, where you have misidentified some object as a tau, or misidentified a jet as a tau, or misidentified a jet as another type of lepton. So these are reducible in the sense that if you did a better job of distinguishing the lepton or the tau, you could reduce this type of background. So it is reducible if you make a better detector or have a more clever detection mechanism. Irreducible means that there's really nothing you can do. It's really the same final state. There's nothing you can do. Okay. So those are the backgrounds. We'll come to the backgrounds that I mentioned in the Higgs ML challenge a little bit. All right, so let's look at the actual events. So the analysis actually is, first of all, divided into sort of vector boson fusion and the boosted. So there are two different sort of analyses, and then divided into the lepton-lepton, lepton-hadron, and hadron-hadron analyses. So and then some of them are not done for various reasons. Okay? And then here are sort of the requirements that they make. So they require, for example, that for the vector boson fusion, that the jets are between, they have at least 40 or 30 GeV or 50 or 30 GeV, depending on which particular final state you're looking at. They said that delta eta, so the eta between the two jets, as I said, they'll have to be forward but in opposite directions, is large. So this is 2.2, 3, so on. Since a lot of the backgrounds come from tops and tops decay to B's, so you can actually reject a lot of the background by vetoing B jets. Now, you can look at a jet and you can tell if the jet has a B quark in it, because B quarks have a lifetime and a decay, so therefore they'll fly a little bit before the decay. So if you look at all the tracks that come out, you'll see a set of tracks that are pointing to a point that is away from the primary point where the interaction happened. That and some other techniques allow you to identify B jets. You don't do a great job, but you can actually do it. So you can veto those things that suppresses your background. And then you can also cut on the PT of the Higgs, for example. I won't go through the boosted, but this just gives you a sense of the type of selections we do. Here's on the right side a demonstration of the Z to tau tau mass versus Higgs to tau tau mass. And you can see that it's a very broad distribution and they're completely overlapping. So the Z to tau tau is an irreducible background. And then this is just another sort of pictorial representation. So you have the two tau, you made the Higgs and it decayed, the two taus go like this, and the two jets, one goes one direction, one goes the other one, and then you have some missing energy that you can calculate that points in one way that corresponds to the sum of the momenta of all the different neutrinos that came out, which way it pointed. Okay. Okay. Now to do this search, of course, it's not just you can't just say I've got taus and electrons. You actually have to look at your data. You have to go through the reconstruction, which takes the raw information that comes out of data, the voltage and things read, and turns it into particle candidates. And then you have to look at the particle candidates and decide if a particular particle candidate is a certain type of particle or not, sort of like what we've been doing in class with LRTPC. So the ingredients are, the various things that go into this are the various algorithms that identify the various objects and reconstruct the various objects. But of course, the very first ingredient is the data. So here's a picture of the integrated luminosity of the atlas in run 1, and for the data that was actually used for the search that I'm going to talk about. So here you can see it's integrated, so you start with very little and you keep on adding, then there was a shutdown, and then you have adding, and keep on going until we got to the full 20 inverse femtobarn-ish data set. Okay? So that's how much the data is. So that's the first ingredient, having data. Then in the data, you have to be able to find electrons, for example, in mu1. So here is the electron efficiency. For different criteria, so loose, medium, and tight, and multi-lepton, these are different requirements. So on the ROC curve, you can, a loose point is somewhere in the ROC curve where the efficiency is high, but a fake rate is also high. And a tight one would be somewhere where the efficiency is low, but a fake rate is very low. So these are just different points on that ROC curve. And depending on what search you're doing, you may pick a different point, as we've sort of just talked about in the problems that you're working on now. So you have to figure out which one you want. So Atlas has defined 3 or 4 points on the ROC curve effectively that are useful, so that we can all talk about the same sort of requirement. So I can say I had a loose electron, and someone else will know exactly what I mean by that. Anyway, what's interesting is that because we have so many collisions on top of each other, when you have you have one collision that makes it a Higgs, but when you have 50 other collisions that give you other things overlaid on that, that degrades your ability to be able to, for example, see the electrons. So here you can see the electron efficiency and how it's decreasing as a function of the number of primary vertices. Primary vertices are the number of vertices you see that each primary vertex corresponds to one collision. Okay. Here is the tau reconstruction efficiency. The taus are actually pretty difficult, and we don't do a very good job in reconstructing them or identifying them. So this is sort of the ROC curve for tau, where there's the signal efficiency with the background, and the point that they picked actually is something over here on that ROC curve. You also have to measure the jets. Here what I'm just showing to you is sort of just the systematic error on the energy scale of the jets. That's actually the biggest systematic on jets that we have, and typically one of the biggest systematics in most analyses. And so this shows you the systematics of these things. And what's interesting here is that since we want to see very forward jets, here this is as a function of eta, it's unfortunately cut off. We're interested in jets that are sitting in this range where we don't have the best necessarily jet measurements. And then finally, you need missing energy. And again, missing energy is, so here's your resolution on missing energy versus the number of primary vertices you get. Again, that degrades. So these are the ingredients. You have to have data, you have to find the leptons, you have to find the taus, you have to find the jets, and you have to have missing energy. Okay, and these are the performance plots. Now, the way they actually did analysis is that after they identified the objects, they would calculate a bunch of features, which we'll talk about a little bit, and then fed those features into the boosted decision tree, and then use that to identify the signal over background. So here you can look at the distribution of a variety of variables. For example, you can look at of course, the mass of tau is a discriminating variable. That corresponds, that's a peak of 125 is the Higgs, right? The delta R is the separation in eta phi space, like I described to you on Wednesday in class, between the two taus. So are the two taus close to each other or not? So you can, for example, look at those. So here it is delta tau tau, and you can see that there is some nominal sort of separation that the Higgs of tau tau decays half. So in this picture, to know how to read it, you see here the red corresponds to what we expect a Higgs. And this one, just because the Higgs is so small, this is 20 times of what we expect from a Higgs. So here's what the distribution looks like for taus. And then the other background. So here is, for example, zeta tau tau is in blue. There's other type of backgrounds. There's a multi-jet background. These are just basic GCD backgrounds. And then the gray area corresponds to the uncertainty we have on the sum of all those things when we put them together. And the points with the error bars are actually what the data give us. So this is sort of an overlay of what the data gives and what we expect to be contributing to this distribution. You can see the signal sits over here, for example. Here is delta eta. This is the rapidity gap. This is the difference between the two jets, the eta of the two jets. And you can see that, for the background, the eta distribution is peaked that way, whereas for the signal, it's relatively flat. So if you're cutting it at above 3, at some range, then you're more likely to get signal events. Other things that you can look at are you can look at the activity in the event. You can see if there was additional things that happened in the event. So this is a vector sum of the PT. Basically says what is the sum of all the energy of all the particles that were there, not vectorial, but just how much energy was in the transverse direction was put there. Here you can see, there's some maybe distribution bound between different sort of objects. And then you can also look at the transverse mass. So you can compute the mass of the lepton with the missing ET and other things, because if you've had a W that you misidentified, if you calculate this, then this would come out to be around the W mass. So you can make a cut on this to get rid of the W, for example, or Z or so on. Okay, so these just gives you a sense of some of the features and what they use. So these are the features. They had two different boosted decision trees, one for the vector boson fusion, one for the boosted topologies, and they use different set of variables. Okay, and then here's what they saw. So after doing all that and taking the boosted decision tree, training it and all that stuff, and then deciding where they're going to cut on it and make a cut on the output of that, then they have their sample, and in that sample they look for, you can look at, for example, the mass distribution to see what the composition of that sample after the selections would be. And here you can see the same sort of plot except in mass. And what you see here is that here are the data points, and here's all the background. So all the background and the little gray dashed area, this is what you expect if there was no Higgs. So this is the sum of all that stuff. And then you see that after all the selections, everything, now you've been able to enhance the Higgs and suppress everything else. So now the red line corresponds to what Higgs would be if it was sitting on top of all that. And then you can see the data, and you can see the data is clearly above the background. So there's clearly something there. Okay. And so here it's just a play here trying to see if it's consistent with 125 GeV Higgs. So you can actually move where you think the mass of this thing would be, and then redo the fit that extracts how many events of that torrent there is. And basically this shows that the best result is when you get, you have the Higgs at 125 GeV, so this is consistent with 125 GeV. Okay. So now you can, on the right side here, there's this new parameter. It's basically the ratio of what you expect the Higgs would be given a standard model to what you actually saw. The expected number of Higgs you see to the the actual number you see divided by the expected number. Okay, that's what you can think of it as. And so you can see that came out to be, so 1 is over here, and so it came out to be a little bit high, but consistent with 1. You can see how it's broken up into different topologies, and then you can see that it's broken up into the different final states and how they worked out. Okay, and the combined all came out to be a little bit higher than expectation, but certainly consistent with that expectation. Okay, and so so you see the this, and you say, aha, we found the Higgs in the tau final state, but unfortunately this doesn't satisfy the criteria. So if you do all the calculations correctly and calculate how significant this particular observation is, you see that this observation only has 4.1 sigma significance. So, and our metric, or the line that we put for what we would claim as a discovery for this particular thing is at 5 sigma. So it falls short of 5 sigma. And it's 4.1 sigma. So there's evidence for something being there, but we can't, to certainty of how particle physicists like to do it, we can't say it's actually there. Here is a plot of the, basically, the Higgs branching ratio, the branch ratio of what's actually observed to the standard model, so it should be about 1 for the vector boson fusion versus gluon fusion. And you can see that this, if you're consistent with standard model, you want to be here, and using the events that we see, we can measure that rate and then compare it to what we expect, and you see here's what we get. And these ellipses correspond to the uncertainty of that central value, and you can see we're consistent with what the standard model would expect. Here is a picture or an event display of a Higgs candidate event. Here, if you look very closely, you can see the 2 jets. So this is the 1 jet, the forward jet, this is the other forward jet. And then I believe, and I have to be, I'm not 100% certain about this, but I believe these things are, so this here is one of the particles that contribute to the tau. So if you look at it very carefully, and so this is looking from some angle, but here you're looking at the cross section of the experiment. This particle here, it corresponds to this. I hope you guys can see this pointer. I'm not sure, but corresponds to this. So I'm pointing to the blue, pointing and green corresponds to the blue and green on the top right. And so you see these circles. So the green circle corresponds to the energy deposited in the electromagnetic calorimeter, and the yellow corresponds to the energy, in the hadronic calorimeter, and the smaller ones, the small yellow, inside of those concentric sort of a circle of sort of these towers emanate from, that correspond to the electromagnetic calorimeter. So you can see this is something that had a lot of hadronic activity. So this was very likely, for example, a pion, so a hadronic pi. And then on the other side, you can look and you can see that here you have something that had a lot of electromagnetic activity. And that corresponds to likely an electron. Okay, so that's event display. And one thing that I just want to mention is that, so the measurements that we're talking about was done in run 1 when we had 7 and 8 TeV. The cross-section for the production of Higgs goes up significantly as you raise the center of mass energy. So at 14 TeV, we have something of factor 2.5 between the cross-section for production of Higgs. So we'll expect for a certain amount, same amount of data, 2.5 times more Higgs is. Okay. All right, so let's come to the Higgs ML challenge itself. And I just want to focus on this one paragraph which describes the data itself. So it says the signal sample contains events in which Higgs bosons with a fixed mass of 223 GeV were produced, so Higgs to tau tau, right? The background was generated by other known processes which can produce events with at least one electron or muon and a hadronic tau mimicking the signal. It's clear from what I've said what that means. For the sake of simplicity, we only consider 3 background processes. Okay, the first comes from the decay of the Z boson into 2 taus. That's the irreducible background we talked about. This produces events with topology very similar that are produced by intrinsic decay, as we described. The second contains a pair of top quarks which have lepton and hadronic among their decay. So the top quarks can go to W's, and the W's can decay into leptons. So then those leptons could be a electron or muon, and the other and a tau, for example. Cycle decay. And the third involves the decay of W boson, where one electron or muon and a hadronic tau can simultaneously occur. Basically what happens is that you get one real electron, muon, or tau, and the other one is some fake that you get from some background that you misidentify as being a real electron, muon, or tau. Okay. The other interesting thing that was relevant to mention is the figure of merit that they use. There's a derivation of this in the note, and I don't want to go through that in detail, but it's in many ways very similar to the measure we're using, S over root S plus B, but I just wanted to point out how to compute these things. There's the one additional parameter that they put in here. This is because, boy, I'm running out of batteries. Hopefully I'll be okay. I got to finish quickly. This additional parameter is there so that if you have low background events, this thing still is reasonable, and they just by hand put that in there. But ignoring that, the S and B are basically your estimates of number of signal and background in your sample. And if you look at this, how you get S and how you get B, as described in the note, the event here, each event has a weight associated with it. And this weight corresponds to various things that have to do with physics, but also corresponds to the fact that any given event, there's a certain probability for that event to come a priori that has to do with the production and the decay boundary ratios and those type of things. And in a training sample, we didn't want to have things at the right ratio to be split up in the data, because the background is millions of times more prevalent than the signal, so then we would have barely any signal if you make a training sample compared to the background. So we make a certain amount of signal and background. But then when you're going to try to estimate something, you have to actually take into account the probability of that particular event being there. So these weights are a way of us being able to recover that. So if you go in your sample and you apply your classifier and you make a subset of that sample that you believe is enhanced in signal, and then you want to compute how many signal events are there, you go through and you sum over the weights of that sample given the signal hypothesis, and that's what it gives you. And similarly, you can do the background. Okay, so by just summing the weights for the signal and background events that you identify as signal and background, you get the signal and background numbers, and that's what you can plug into here. Okay, I just wanted to point out that there's maybe a little bit of confusion, but there's different things that correspond to somewhat the same thing, which I mean is the number of signal and background events you have. You have the expected number, the one that you calculate. You have the observed number, the one that you measure. And those observed numbers you can get in different ways. So one way of estimating it is doing this, but another way of doing it is by just calculating, seeing how many total events you have, this mu s, how many total events you have, subtracting what you expect the background would be, and the remainder is what the signal is. This is sort of like what I did in class. Okay, So the last slide, I just wanted to list all the features are there, all the variables they give you. There is the sort of, I would say, the raw data. This is corresponding to the same things that you were doing in the last lab. These are the 4 vectors. So these are the 4 momenta, or you consider 4 momenta of the taus and the lepton, the missing energy, and the 2 jets. The leading jet means the highest PT, and subleading jet means the second highest PT. So these are all the kinematics for those things. And there's also the weight and the truth label that's there. Beyond that, there are a variety of variables that are featured variables that are physics motivated to be there. So event ID you can ignore. It's just a way of identifying unique events. Here, for example, this is the mass of the Higgs, which you can compute given all these sort of variables. This is the transverse mass you can compute, which is sort of different quantities that allows you to suppress W's, for example. This is the invariant mass with a tau and a lepton. All these things are sort of trying to capture particular decays where something had decayed to give you the same final state, but if you reconstruct it, you'll see that it's something of a lower mass than the Higgs mass. Okay. Anyway, you have the PT. I explained this very well earlier. The sum of the PT of the particles. This is the delta eta. There's a rapidity between them. This is the mass of the jet system. This is the product of the pseudo rapidities. For some reason, it's a good variable. I'm not quite sure why. The separation between the leptons. This is again some sort of variable. The various variables that have the sort of the sum of the PT of the objects. The ratio of the lepton to of the PT of the lepton to the tau. There's also a measure of, so as I explained, that the events have to be, the 2 jets are very forward, but the rest of the things, the Higgs, the taus have to be very central. So here's 2 different ways of measuring centrality. Here, the first variable measures how central was the missing energy, and the second one measures how central was the leptons they observed. Okay? All right. So I don't really have an assessment of how well you guys are doing right now and how far you've gotten. I hope that you are making progress towards your exam. If not, you guys are going to have a pretty tough couple of days to pull it all together. I will. What I'm going to do is I'm going to post this video and send an email to everybody because they know the video is there, and then I'll also let you all know that I will later on today at around class time will be available over Google Hangouts, and when I'm available I'll send an email to the link to the Google Hangouts so people can join me, and then you guys can ask your questions. All right guys, thank you very much. Bye.